Tonight's presentation provides a simplified understanding of four-dimensional space-time and will present some of the evidence to support it, including methods of graphically work out space-time distortion without the use of math. Disclaimer, there will be some math, but Tim doesn't have time to wait for everybody to do it, so he'll do the equations for us. Tim Campbell has been interested in astronomy for as long as he can remember, but became completely hooked after observing Saturn's rings through a telescope when he was 19 years old. He has been a member of the Ford Astronomy Club since 2011, enjoys public outreach, and is a planetarium presenter at Henry Ford College. Having enjoyed viewing objects of the night sky, his interests are steered towards understanding the physics of the cosmos. Let's welcome and give a big hand to our past president, Mr. Tim Campbell.
I am not a professional physicist, so when it comes time for Q&A, go easy on me. All right. One of the disclaimers I want to throw up in front is there will be some lying going on during this presentation. I promise that after the lying is completed, at some point I will tell you that I actually lied. Some of the concepts that I'm going to explain are actually easier to explain if we tell lies. All right, so this is, you'll find this presentation is going to meander a bit, and you're going to wonder where I'm going with this. It does all come together, trust me. The other thing I wanted to mention is it's not actually a presentation on special relativity. So there's no way to talk about space-time without talking about special relativity, but you can find loads of documentaries that talk about special relativity and all the weird things that happen in special relativity. I specifically wanted to talk about the time distortion concepts, and so I'm going to sort of ignore some of the other stuff. If some of you want to inject with some comments from time to time, go ahead. There's a lot of content to get through. I've rehearsed this a couple times. It's going to take every bit of the hour. All right, so starting out with the speed of light, one of the first beliefs around the speed of light was that light travels without delay, right? So who thinks that? Well, it turns out Aristotle thinks that. Aristotle also thinks that if you drop a 100-pound cannonball and a 1-pound cannonball, that the 100-pound cannonball drops to the ground 100 times faster, which turns out not to be true. Nobody checks, it turns out, for 2,000 years. So Aristotle doesn't get everything right. But René Descartes also thinks so, and so does Giovanni Cassini. And it turns out loads and loads and loads of other people think so too. So this was the going wisdom of the age, is that there is no speed of light. Light is just an instant phenomenon. It was understood that sound was not instant, but light is an instant thing. All right, well, maybe. There is a holdout. So this guy comes along, and it turns out he's been fooled by Aristotle before, so he decides he's going to do some checking. So this is what he decides to do. He finds a place where there are a couple of hills separated by some considerable distance. These are probably not the hills. I just needed a picture off the internet of a couple of hills in the English countryside. He needs to send some people up to the top of these hills, and they need to be carrying some lights. So we'll drop some lights onto the top of the hills. They're going to shield the lights so that the observer on the other hill cannot see the lantern. So I'll put some cards to block the lanterns. Now here's the game. Observer number 1 will drop their card so that their light can shine and be seen by observer number 2. At the very instant that observer number 2 sees that light show up, they're to drop their card so that their light shines back to observer number 1, and somebody will time this and figure out what the round trip time is. After doing this experiment many, many, many times over, Newton concludes that either light actually is instant, or, to Newton's credit, it is simply too fast to be measured with the means that he has available. So he still doesn't necessarily concede that it's instant. He just says, hey, in this era, we don't have the ability to measure it. And that's a possibility. All right, so changing gears now, and you're really going to wonder where I'm going at this point. I want to talk about the longitude problem. How many of you read the book Longitude? So a couple of you kind of know the story. All right, so the longitude problem factors into our story. You'll see how eventually. If you want to find out what your latitude is, that's pretty easy. All you do is on a ship at sea, or frankly on land, if you really wanted to, but they were generally done at sea. all you need to do is hold up a sextant, look at the North Star, measure the angle from the horizon line to the North Star. There's your latitude. Easy peasy. So sextant, take the measurement, you're done. Finding your longitude, however, now that's a different problem, because if you pointed toward a star in the eastern horizon, well, stars are rising in the east and setting in the west. So you kind of have to know what time it is. And the problem is, the ships, or the clocks of the day, mostly run on pendulums, the accurate ones do. Pendulums don't work so well on ships, it turns out. So when you don't know where you are, it turns out bad things happen. So, one of the most famous stories of bad things happening is this guy. He had just finished winning a victory at sea for England. He was coming around a point on the southwest corner of the country. It was around 8 o'clock at night, but it was, I want to say November. It was at a point, of course, there would be no daylight saving time in that era. It would have been dark. They did not have the electric light. So there was no way to see land. There was a reef and some islands that they knew about, but they thought that they had steered clear of this. It turns out they had not. 4 of his ships were sunk, 2,000 lives were lost, including his, by the way. But there were lots of merchants that had been petitioning the crown, you need to solve this longitude problem. We keep going off to trade with other islands, and we miss the islands completely, and we're having all these problems. Right? So this is the longitude problem. So it turns out the Board of Longitude is formed by royal decree in 1714. And this board is going to solicit ideas for working out the longitude problem. Anyone who can solve this problem is going to be a very, very wealthy person. Tens of thousands of British pounds were going to be paid, and that was back in those days. So this was quite a prize. It was considered to be a king's ransom for solving the problem. If you've read the book, if you haven't read the book, read the book. It's a short book, it's an easy book. There's a lot of quack job ideas. Probably the quackiest idea that I remember reading in the book was they were to take 2 dogs with some sympathy powder or something. The idea was they would put load one dog on the ship and send that dog off to sea with the sailors. The other dog was to stay home at the home port. And when it was noon on the day of the home port, noon on the day, they would torture the dog in the home port until it yelped. And then magically this sympathy pain would be felt by the dog at sea, and it would yelp at the same time, and that's how you would know it was noon. Sounds reasonable, right? Okay. So it turns out to solve this problem, you need to know the correct time at a fixed location on land. Right? So for example, here we are in Dearborn, Michigan. We could say, hey, at 10 p.m. tonight, on this day, we know that Vega is going to be a certain altitude above the eastern horizon. Now, it'll be at a different altitude tomorrow, and it'll be a different altitude yesterday. But today, we can know what it is. So if you knew what day it was, and you knew what the altitude of a known star would be at a specific point in time, and you knew what time it was, then you would be able to measure that same star and say, oh, that star is 5 degrees lower in the sky. That must mean I'm 5 degrees farther west. So this is the general idea, but you do have to know the time. So, of all the quack job solutions, one guy comes up with one of the solutions. Turns out not to be the winning solution, but he did his best. We know this guy, Isaac Newton. His idea was to use the occultations of the Jovian moons. And here's how this works. It turns out, Io orbits Jupiter. Who said that they wanted to see the transit of Io? Okay, there you go, Bob McFarland, right? Io does this every 42.5 hours, roughly, right? Now they've got it down to the second. 42 hours, 27 minutes, 33.5, right? So they've got this down. So the idea is, all we have to do is make some tables. And the tables will say, on this day, Io will occult at this time, so it pops behind Jupiter, and we wait for it to pop out from the other side. And we know exactly what time that will happen as it would be from our home port. 42.5 hours later it does it again, so we'll make the next table and the next table and the next table. And we'll do this going out for 5 years, 10 years, how long are ships away at sea and come back years later. So we have to have tables that are long enough. So they write up the tables. Easy peasy, problem solved. Well, sort of solved. Trying to see Io transiting Jupiter on a ship floating at sea could prove to be problematic, but they have an invention. And here it is. It's called, I don't know how to pronounce this. It's probably calotone. Could be cellatone, I don't know. Anyway, the idea is you wear this doohickey on your head. Look, there's even a candle there, just in case you need some light to see why you're doing this. And you wear this doohickey on your head, and you can use this to sight Jupiter and watch for the occultation of Io or any other Galilean moon that happens to be in the tables.
And if you're far enough south, the wax pours out of your head as you look up.
So, all right. And then you watch this happen, right? So, does need to be a clear night. Oh, and by the way, it does need to be night because a lot of times those 42 and a half hour periods, a lot of times Io is doing this during the day. But you could probably find, hopefully, something happening at night every few days. So maybe you're lost for a couple of days and then you figure out where you are. So that's the general idea. Problem solved, right? Well, not quite. They decide they should probably test these tables. That might be a good idea. And when they do, they discover a problem, which is that Io fails to obey the orbital rules as prescribed by Kepler's laws of planetary motion. Specifically, what happens is that on some days, Io emerges too early, as much as 8 minutes earlier than what the tables predict that it should happen. Some days, Io emerges 8 minutes late versus what the tables predict that it should do. These guys are racked trying to figure out why does this moon speed up and slow down as it goes around Jupiter. They have confidence in Kepler's laws that this should not be happening, and yet it is happening, right? So they can't deny that. So this guy notices an interesting coincidence. This is actually kind of interesting. To tell you what the coincidence is, I need to draw a miniature solar system. So we'll just pop the sun in the middle, we'll pop Jupiter and Io off to the side there. We have to pop the Earth in, and I'm going to draw a little blue circle to indicate the orbit of the Earth as we go around the sun. And it turns out that when Io is at this position in the orbit, Io occults as predicted. The tables are right. So that's not a problem. But when Io is over here...
I think you mean Earth, not Io.
I'm sorry, Earth, thank you. Thank you for the correction, Earth. When Earth is over here, Io occults 8 minutes late at conjunction, roughly 8 minutes late. But when Earth is over here on the other side at opposition, Io occults about 8 minutes early. Romer thinks this is too much of a coincidence. So he comes up with this crazy idea that maybe, just maybe, light actually has a speed. And that Io, it isn't Io that's speeding up and slowing down, it's that it takes light longer to get across the solar system when Earth is on the far side of the sun than it does when Earth is on the near side of the sun. So that's the idea, right? Of course he is scoffed at because he is going against the conventional wisdom. Every idiot knows that light is instant and travels without delay. Lots of famous people said so. So it turns out the best way that you prove that somebody is an idiot is by trying to reproduce their work and prove where they went wrong. And when you do that, you find out that they're right, and then you co-opt the idea and say, I knew it all along. So it does become accepted that light has a speed after all. Now, at this age, they don't know how far the sun is from Earth. They take their best guess. Romer comes up with an idea for the speed of light. Turns out he's something like 70% of the speed of light. It's way off. It's not close. But you have to give him some credit for working out the problem. And in his defense, they had no idea how far away Earth was from the sun. There had not yet been a transit of Venus measurement. Okay, next topic, light's wave nature. So the question about light is it a particle or is it a wave? Now, no spoilers for those that know the answer. Very smart guy, we know this guy, we've seen him a couple times in our presentation already, writes a paper on it called Optics. And in Optics, he says it's a particle. Now, one of the reasons that he believes that it's a particle is understanding gravity and that the gases probably clump around the planet and that's what causes us to have an atmosphere. There probably isn't actually air out in space, and that means that light has to travel through a vacuum. and waves don't typically travel through vacuums, and so therefore it couldn't possibly be a wave because there is no medium in space. It must be a particle. So he comes to this conclusion. Thomas Young, on the other hand, does this experiment called the double slit experiment. He's the inventor of it. He does it a little bit differently than most people think of doing the double slit experiment today. But the punchline is he notices a wave interference pattern. And so with this wave interference pattern, actually I'm going to turn something up here. Okay. He notices a wave interference pattern and says, it's doing a lot of stuff that behaves in a wave-like nature. All right, so here, and I hope my speakers work. I meant to bring some separate speakers for this, so I'm not quite sure this will work. But for here, I have a sine wave. So here's the, not much math, just a little bit, so don't panic. X is the sine of y. So this is just a very simple sine wave function. With this, I get this very soft, gently rolling wave. Now, this isn't very good for audio purposes because the wave frequency is too low to be detected. So we need to speed this up a little bit. So to speed it up, I'll use a different function, which is x equals the sine of y times 10. Now, 10 hertz would be below what humans can hear, but if I use like 400 or 500 hertz, that would just look like a solid line going across. The squiggles would be too frequent. So I'll just use x is y times 10, and I get a more frequent wave. If the speakers work, you should be able to hear this. Here we do. Okay, you all heard the sound, right? Great, perfect. Okay, here we go. Now let's change this a little bit. Now I have a blue line, it's not exactly the same. X equals y times, we're getting tricky, 11. Ours goes to 11.
Ooh.
All right. And so if we play this wave, we hear this sound. Okay, everybody hear the difference? All right, so it's a slightly higher pitch. Not much, just a little bit. Now what happens if we overlay the two waves on top of each other? So the red line is x's times 10, and the blue line is times 11. And what I really want to point out, and I forgot to pull my laser pointer out of the bag, is that at this point here, the waves are exactly on top of each other. They are here as well. They're over here as well. So the waves are stacking on top of each other. But they don't have exactly the same frequency. So here, the waves kind of oppose each other. They oppose each other here, they oppose each other here, and they oppose each other here. So sometimes the waves agree with each other. They line up nicely, and sometimes they oppose each other. All right? So listen to what happens. Okay, that was not a special sound effect. I didn't do anything weird to make that sound. All I did was play both of the two waves that you just heard. I just played them both at the same time. And that's what you heard. So who was here when we did the LIGO? I actually wasn't here for it. Right? Wave interference patterns. Okay? This is wave interference. So this is interferometry, if you will, measuring waves interfering with other waves. Except instead of doing light waves, we're going to use sound waves, because it turns out light waves are so fast that your eyes wouldn't see the difference. But sound waves, those are so infrequent that your ears easily actually pick up the sound. So what's actually going on is when you play two waves at the same time, you simply add them up. So here's what that looks like. This is what we're drawing. The green line is what we're drawing here. It's simply adding them up. Sine of y times 10 plus the sine of y times 11 at the same time. Literally, I went into the software and typed in this equation, and that's what it draws, which is the green line. If I take this away, take away the red and the blue, so now you're not distracted, what you see is where the red and blue lines agreed with each other, so they had a value about +1 or -1, it doubles to about +2 and -2. So I get a real strong extra loud wave, but where they oppose each other, they cancel out. So when the X wave is, or when the red wave is on the +1 value and the other wave is on the -1 value, well, +1 and -1 is 0. And so they literally cancel out and they intersect at that point. And this ends up sounding like a sound which gets louder, quieter, louder, quieter, louder, quieter. And I'll play it again. Okay, so there you go. You now are experts on interferometry and wave interference patterns. Got that? All right. So now we're back to this problem, which is that waves do now require a medium. Remember, Newton said, well, it's got to be a particle because there's nothing in space, so waves can't go through space. So enter Christian Huygens. Christian Huygens says, I'm going to redo this experiment in my own way. Some key things I need to point out here. He's got his two slits. Now I've drawn this value of light in yellow and this one in green. It's important to let you all know that in order for this experiment to work, you cannot use different wave frequencies. They have to be the same frequency. Like if you just did white light, which is like the whole visible spectrum, this experiment would not work. So typically you're going to use a single color of light, run it through a prism, take out one of the colors and send it through both slits. But here's what we're going to do. We're going to run it through and I'm going to draw the waves and I'm going to show them piling on top of each other here, just a few of them. What I'd like you to notice is that if the green, this would be like the peak, that would be the next peak, that would be the next peak. The black area in the middle, those are the troughs of the wave. So you've got peaks and troughs coming into these waves, and the same is true with the yellow. And notice here that the yellow and green line up, yellow and green light up, yellow and green light up. And here, you've got yellow and green here and yellow and green here. Actually, let me just draw it for you. And you see how they nicely line up with that. Now notice we're getting bright light here where they intersect, where these things line up, and here. But here, where I'm between this green peak and this green peak, is the green trough. And the yellow peak goes through the green trough, and so they cancel out, and so you get a dark region. Okay, so now we're sort of drawing the wave interference pattern there for you graphically, so you can sort of see what's happening with this. And this would be what you would see if you did the double slit experiment. Huygens confirms that yes, indeed, it is a wave nature to light. So light, it turns out, is a wave. But we need that medium. All waves need a medium. Sound needs air or some gas to go through. Water waves need water to go through or some liquid to go through. So light waves must have a medium that has yet been undetected. So they invent the medium and they call it the luminiferous ether. Problem solved. So it seems. Let me draw up what the luminiferous ether is going to look like. So here's my little mini solar system with the sun and the earth. And I'll draw the ether. They realize that we're going around the sun's going around the galaxy. Probably the ether is not stagnant. Probably parts of the year we're plowing into it, parts of the year we're running away from it. And therefore, if your wave is propagating through a medium and you're heading upstream, upriver, that wave will seem to repeat more frequent. When you're heading downriver, that it'll be propagating more slowly. So you'll see a difference in the speed of light depending on whether you measure the speed of light in the summer or the winter. Now they don't actually know which direction it's going, but they just assume that they'll find a difference. If you wait enough months, you will find a difference. So the guys that are going to do this are Albert Michelson and Edward Morley. This turns out to be one of the most significant experiments ever done in science. Here's the gizmo. They've got this doohickey here, which is going to shine some light. It's going to hit a mirror that's semi-silvered. It's going to send half the light one way, half the light goes straight through, bounces off some flat solid mirrors at the other side, back toward the center, and back into this detector, and they hope to see the wave interference pattern. Right? By the way, here's a photo of what it actually looks like. For some strange reason, you can see all the material on top of this table. The table is actually a massive stone slab, which for whatever reason they decided needed to be floated on a pool of mercury. Not that that would be dangerous.
Isolates vibration.
Yeah. So, okay, perfect. So, and there's no need to worry about the liquid mercury. All right.
Oh, no, of course not.
So what are the results? Anybody know? Somebody knows. Yes.
Well, I know.
Few of you know. The greatest null result of all time in science. They get nothing. They get nothing. You must have done something wrong. Surely you would have been able to detect a difference. Lots of other people try, they do the experiment over and over, they do it at different times of the year, they have other people that do the experiment, people try and figure out what's going wrong. No matter who measures the speed of light, and when they measure the speed of light, and where they measure the speed of light is always the same, and you can never measure a difference. So this is kind of, so now the plot thickens, right? So let's take a checkpoint. Light turns out to have a speed, doesn't travel instantly. Light is a wave. Also, by the way, it turns out to be a particle. I didn't want to go into the whole particle part of physics, but it turns out it is both a particle and a wave. for mind-bending reasons. And light is able to propagate through space and does not require a medium to do so, the only wave that we know of that can get away with that. And the speed of light is always measured to be the same for everyone, for all observers, everywhere, no matter when they take the measurement. All right, so this has some perplexing consequences if all of these things turn out to be true. So this guy comes up with an idea that if the speed of light is always the same no matter what, so if you're standing still and we measure the speed of light and we come up with a speed, and someone else is going 1,000 miles an hour and they measure the speed of light and they get precisely the same speed, and you would intuitively think, well, it should be that speed plus 1,000 miles an hour or minus 1,000 miles an hour, depending whether they're heading toward it or away from it. Something else must be going on. And Einstein says, yeah, what's going on is it's the nature of time that we all assume to be constant is in fact not a constant. It's time that is being bent. All right? So the book that he writes on this, or the paper he writes on this, I think he wrote 5 papers in that year, four papers at least. They call it the miracle year for Einstein because he wrote so many seminal papers in that particular year. But this paper is called The Electrodynamics of Moving Bodies. It is the paper that we all refer to as special relativity. So special relativity comes before general relativity. Postulates these two things. The laws of physics are the same for everyone, easy enough. And number 2 is the speed of light will be measured to be the same for everyone. And I sort of added in my own accent, everyone, everywhere, and every when. Turns out to be true. This theory ends up reconciling Maxwell's equations of electricity with the laws of mechanics. And so this unifies space and time and light. And so Einstein says it's not space and time, it's simply space-time. It's one thing. It's not two different things. There's one thing, and it's called space-time. And this is sort of the point of the presentation, is to help you sort of understand that. By the way, it's called special because it does not account for the effects of gravity. And it turns out to do this accurately, you do have to account for gravity. We're not actually going to get into general relativity at all, but I'll just mention what it is. It reconciles all that other stuff and adds gravity in as well. I'm not going to cover it in the presentation. This is a famous quote that sometimes gets attributed to Einstein. It's actually John Wheeler who said it. Space-time tells the matter how to move, and matter tells space-time how to curve. This wouldn't be complete without mentioning this guy, Hermann Minkowski. How many of you have heard of him? See, not just a couple of you, not many of you. It turns out Minkowski is one of Einstein's teachers, or was at one period in time. It isn't that Einstein was not a good mathematician, but Minkowski, he was the mathematician's mathematician. He was a much better mathematician than Einstein, absolutely outstanding. So he's looking at Einstein's work with all of these equations, and he is able to visualize things that even Einstein can't visualize when he's looking at these equations and says, oh yeah, you know, if you rewrote this in another way, what you would see is that space-time is this constant vector. And you could literally take like a coordinate system and tumble it around and be able to show all these really cool things with it. And so they come up with a name for this thing called Minkowski spacetime. We'll get into this just a little bit. All right, I'm just checking my time check. All right, now I said there would be no math. Don't panic when you see the equation. What you need to get out of this, and you don't need to worry about what all of this stuff is per se, but this is something called the space-time interval. So in space-time, and I don't have a slide on this because this is an easy concept, between any two events, you could have one person observing the event from their reference frame, their speed, their location, there, fill in the blank, right? And you have another person, and they are witnessing the same two events from their reference frame, their speed, their location, and all their stuff, right? You can define something between those two events, which we'll call the space-time interval. Delta S is the space-time interval. This is a constant. For these two events, it will be a constant. For all observers of the event, the space-time interval is the constant. That's the thing that never changes. Delta t is the difference in time between when each observer perceives these two events occurs from their reference frame. Somebody else would see these things occur at different times from their reference frame, and that's okay. Delta x is the distance between the location of the two events. So an event is simply something that happens at a certain time and a certain location in the universe. We call that an event. So if a supernova goes off in another galaxy far, far away and we all see it, the location is the galaxy far, far away, and the time is when we all see it. From our reference frame. If you were in another galaxy witnessing the same event, you would think that it had a different time and a different location. But if you did the math on this, we'd all come up with the same delta S. C is a constant for the speed of light. You don't need to worry too much about that. All right? There are different ways, by the way, to draw this, so more on this later. Okay. Here comes a very easy analogy that I think hopefully everyone will get. I'm going to draw a little graph, and across the bottom, I'm going to measure miles from 0 to 10 miles driving east, and 0 to 10 miles driving north. We'll make this journey on a bicycle because we only want to go 10 miles an hour. And so here's how this works. Easy question for everyone. You'll all get this. You travel 10 miles north on your bicycle at 10 miles an hour. You've been traveling for 1 hour, right? So I've got this vector I've drawn in red. Let me just highlight this. How far north have you gone after the hour is completed? 10. That's easy. Part 2 of the question, a little bit trickier. How far east have you gone? 0. Okay, you're all with me. This is working well. Better than I thought. All right. New example. This time we're going to ride our bicycle from our origin point east. Again, we're going to go 10 miles an hour. We're going to travel for just 1 hour. At the end of our 1 hour, the question is, how far east have we traveled? 10 miles an hour. And how far north have we traveled? 0 miles an hour. Okay, awesome. This is really working well. Now we're going to get really tricky with this next example. Try and hold it together. Now we're going to go 10 miles. We're going to travel northeast at 10 miles an hour for 1 hour, right? So at the end of our hour, how far north have we gone?
7 miles.
7.071. It turns out it's the sine of 45 degrees, right? And it turns out to be basically 0.7, right? So we've gone roughly 7 miles north, and we've gone roughly 7 miles east. Trust me, there's no Photoshop magic going on here. The orange line is exactly the same length as the green line and the red line. I've done no trickery. This is not the part where I'm lying to you, at least not about this. All right. Okay, perfect. Now, let's just change some terms here a little bit and redo our exact same graph. Same graph, you saw this before, you're familiar with this exercise, except now we're going to make the y-axis mean time, and we're going to make the x-axis mean space or distance. Our favorite way to represent time is to count it in years. Bad things happen when we try and do this in minutes, hours, seconds, months, especially months, because months are all different numbers of days in each month. And our favorite way to represent space is in the units called light years instead of miles or kilometers or whatever. So we'll use years and light years. There's a reason that I'm going to do this that will become apparent later. All right, so if we sit in one spot and we do not move for 1 year, you might want to go to the bathroom before we start this.
Yeah.
All right, after 1 year, what happens?
You've gone vertically.
You have now moved 1 year through time. That's what you've done. Easy, right? So just sit here for a year, you've moved 1 year through time. All right, now the tricky part. This time we're going to travel at the speed of light for 1 year. What happens to you at the end of your year when you've traveled 1 light year at the speed of light? You have changed your distance by 1 light year. By the way, time has not passed for you. The time has stood still.
So much you miss the LF travel?
Yes.
Yeah.
Trade at light speed.
Listen, I'm doing my part to save the planet by not wasting unnecessary L's.
Yes, and pixels.
That's what I'm going with. All right, so if you can travel actually at the speed of light, we'll talk about if you can in a bit, but if you can, time does not occur for you. So when you see light coming from the Andromeda galaxy 4.2 million light years away, and you think, oh, it took that photon of light 4.2 years to get, or 4.2 million years to get here. No, that photon of light was simultaneously released from some star and absorbed by your eye in the very same moment. Time did not pass for that particle of light. Okay, so that's the trade-off. So as Liam uses the example, it's like having some money and two accounts that you can deposit it in. You can deposit a little bit of your money this way and a little bit of your money that way. And then the tricky part is, what if you did a little bit of both for a year? You get that line and it says, oh, okay, well, after 1 year, you would have only have gone about 7/10 of a year through time, and you would not actually have made it a true light year through space. Everybody agree with that? Okay.
No,
I'll take your word for it.
No, I like to say that. I like to say that it's like you have, like Tim said, you have currency, and you can use your money to move through time or through space all at once. If you want to put all your money into time, you only go in time. If you go to put it into space, you only move through space. But to move through time and space, to actually move at a speed and get somewhere, you're moving through time and space. You have to divide your money. So the theory behind it is, we're always moving at the speed of light, but we're sharing it between moving time and space.
You're getting out of the presentation. All right, so Chris has a problem.
Yeah, I got a problem. Light years actually is a distance.
Correct.
Well, you're presenting it as time.
Have I really? Wow.
No?
I refer you to slide number 2 in the presentation where I said that I was going to be lying to you from time to time. It turns out I just lied to the entire room. All right, so this is a bit of a fib. Why did I do this though, right? This explains space-time using the geometry of a circle. And it turns out if you try to use the geometry of a circle, though intuitively our minds grasp the concept, you will actually get the wrong values. So it doesn't actually work. So good job, Chris, for calling me out on that. It turns out it does use the geometry of a hyperbola, but the most important part of this is not that you understand that it's a hyperbola, but that you understand the concept that you can actually trade time and space and play them off each other and decide how much progress you want to make through space versus how much progress you want to make through time. And that concept, that part I am not lying about. That part is rock solid science. Okay, so now all about hyperbola. By the way, the plural is hyperbolas, or hyperbolae. It's just not hyperbole. Anybody know why?
Oh,
Anyway. All right, I got to grow out of it. All right. So, remember I mentioned the space-time interval before? Remember I had the radical sign? And there's no radical sign. I said, oh, there's lots of different ways to, why don't I have a radical sign? Well, because if you square this side, you can just get rid of the radical sign. But that means you have to square that side to keep it equal, which means that the delta S has to be squared. So this is another way of representing the space-time interval. And here is the formula for a hyperbola. So if I take something squared minus something else squared, it will equal a constant, which we'll represent with k. Depending on the hyperbola and where we want to draw it on our graph, it's equal to some constant. So the constant never changes for all the points on the hyperbola. It turns out you see something squared minus something else squared, and it equals a constant, which in our case is the space-time interval. Now the space-time interval is squared for reasons that we'll get to, but you can see the similarity here. So the mathematicians looked at it and said, yeah, that's a hyperbola. Now there's a way that they came up with the, I'm not going to get into how they found out that that equation was the right equation, but there are other things on special relativity that do get into how that turns out to be the answer, because that's probably more math than we want to cover here. All right, so with this, so I've got the space-time interval. Notice this c over here. The c is the constant. and that constant is the speed of light. Now, whenever you see a constant in an equation, you really should just think of it as a conversion factor. So if I said 1 foot equals 12 inches, that's a conversion factor, right? So if you wanted to convert from one to the other. If you didn't convert, ratios and proportions and things would work out, but you wouldn't actually get the correct answer. So it turns out you could ignore this 1 over c, and the concepts would all work out, you just wouldn't get to the exact right answer. But there is actually a way to cheat on this a little bit. So c is the constant for the speed of light. It is a conversion factor. C could be 299,792,458.0 meters per second. That is precisely the speed of light, and there is no round-off error in that number. Anybody know why?
They defined the meter.
Because we redefined the meter to be one. We redefined the meter in 1983, I think is the year we did it, so that there would be no point anything on there. So that turns out to be a bit of a cheat that science did. It could also be 186,000 miles per second. By the way, there is a point something after the decimal point when you do it in miles. I'm just not going to write it. But c could also be 1 light year per year. That would be correct, right? For the speed of light. Speed of light is 1 light year per year. So I could write it this way if I wanted to use this particular unit. Well, what happens to the equation if I use 1 light year per year as the unit? That becomes 1 over 1. Well, what's 1 over 1? Well, that's 1. What's 1 times any other value? The same value. So in other words, if I represent c as light years per year, I don't have to do 1 over c. I can just sort of cross that out of my equation. So that's kind of tricky. All right. Now, here comes the fun part. Graphing space-time without using any math at all. So for those of you who bothered to flip your sheet over, did anybody flip your sheet over, your agenda? And you notice this funky looking graph. All right. So this is how you're going to solve space-time equations without using any math. All right. So first I want you to understand that in our hyperbola, we've made all of our units intersect in each whole point on the grid. You notice that equation, it was x squared, or I'm sorry, delta s squared instead of just delta s. It turns out if you just use integer values for delta s and you don't square them, these dots don't line up on whole units. So if I said that it's 1 squared, it turns out it ends up on the 1, turns out it would end up on the 1 line even if I didn't square 1. But 2 squared won't end up here unless delta s is 2, won't actually put the dot here. I have to do delta s squared to get it to show up there. So just so you know what I'm doing. All right, next. The hyperbola asymptotes toward this 45-degree angle. That is to say, you see everything sweeping into this direction. It's heading up at a 45-degree angle. To asymptote, for those not familiar, means that we're going to approach that line without ever touching it. And I do actually mean infinity. Doesn't matter. You could go 1 trillion light years away, and these lines never actually touch. They get ridiculously close, but they never actually touch. And that's what it is to asymptote. It's kind of like the 50% of the football field game where you say, I'm going to start on one end zone and I'm going to go 50% of the way toward the other end zone. And then I'm going to go 50% again, so now I'm on the 25-yard line. Now I'm going to go 50% again, so now I'm on the 12.5-yard line. And how many 50% movements does it take to reach the other end zone? And the answer is never, because you keep dividing it by 2. So it's the same game here. It just keeps getting ridiculously close without ever touching it. All right. The origin is going to be this point down here where you can kind of see it all comes together. So for anyone who's going to use this as a reference frame, that's kind of your starting point. The speed of light, c, is the constant that would be represented by the middle of that asymptote angle, that 45-degree angle. All right. The y-axis is going to represent time. It could be in any units you want, but trust me, it is a lot easier to do the math if you represent it in years, because then you don't have unit conversion problems when you're doing your math. And then distance will represent along the x-axis, and it's a lot easier if we just do that in light years. So here comes our example. I'm looking at how much time I have left. Now I've just sort of zoomed in on the lower corner, so it's a little easier to see the grid lines, because I'm actually going to draw this on the board for you as we go. All right, so we have 2 observers. We'll call them Mary and Bob. It doesn't really matter what their names are, but Mary is going to be our observer, And so for this example, this is Mary's reference frame, and this is our origin event, right? Always in that corner there. That's our origin event. So that's one of the events in the space-time graph. And then Bob. We're going to send Bob out at 2/3 of the speed of light. Okay, so to draw 2/3 of the speed of light, that's this red line here. But how do I do that? So for those who are a little sketchy on their math class when we used to do this, normally you would go up 2 units and over 3. But if you did that, you would get a line that ends up in sort of this part of the graph here. We would prefer it to be in this part of the graph, so what we're going to do is just invert that. So 2/3 of the speed of light means I go over 2 and up 3, and notice it intersects. Over 2 and up 3, and it intersects again. Over 2 and up 3, and you notice it intersects again. So that is the slope of 2/3 of the speed of light. If you wanted to go 99% of the speed of light, then you would go over 99 and up 100. And you'll need a bigger piece of paper than I gave you to be able to do that. But if you wanted to do the graph for 99% of the speed of light, certainly knock yourself out. If you wanted to do 50% of the speed of light, then you would go, that would be 1/2, so you'd go up 2 and over 1, up 2 and over 1. That's the inverse of 1/2, or 50% of the speed of light, and you get that slope. All right, is everybody with me? We're okay? All right, good. All right, so Bob is traveling at 2/3 of the speed of light, and Mary now believes that Bob has been gone for 10 years. Mary believes this is true. Bob has been gone for 10 years. So the question is, so now we have to add Mary's vertical slope and a new event point for Mary. So remember, Mary hasn't moved, and we've already established that if you don't move, you don't go through distance at all, but you do still travel through time. So Mary has traveled 10 years through time, and so that green circle up there, that's Mary's second event for her. That's where Mary ends up. And now the question is, how much time has elapsed for Bob? And so to find this out, what we need to do is figure out where Mary's line there intersects with Bob's line there. So we've circled that point. I did dashed greens this time, and we've got another intersection point. All right, here comes the really hard part. How many can count to 10? This is going to be really easy. All we have to do is count how many times Bob's red line crosses a hyperbola. 1, 2, 3, 4, 5, I probably should have made this animation a little bit faster, sorry. 6, 7, and we run out, right? And then we get to the event. Okay, so that means that Bob thinks that there has been 1, 2, 3, 4, 5, 6, 7, and part of a year. I'm going to say that that's a little less than a half a year, maybe 7.4 years. But to my eye, that looks like it's about 7.5, actually just a tiny bit shy of 7.5. Easy enough? Okay, so this is space-time distortion. And by the way, this time I am not lying to you. This actually does work if you do this. And it is this easy to graph. So are we correct? All right. If anybody has a calculator in the room that can do squares and square roots. All right, here we go. Jessica to the rescue. All right. Jessica has a degree, so if anything goes wrong, it's definitely her fault. All right, so what distance does Bob appear to have traveled? We can drop this line straight down to find out how far Bob has made it in this amount of time. He was doing 2/3 of the speed of light, so it turns out he's gone about 6.66 light years. So let's try some math. And here's the equation. Jessica, you can help us out with this. What we need to do is take the difference in time for the events, and that turned out to be 10. So that's 10 squared. 10 squared is simply 100, right? So I even used easy units. So 10 squared is simply 100, minus the quantity of 1 over c. But remember, we decided that c is going to be 1 light year per year, which means that that's just 1, which means we don't have to do that part. We can ignore that. So it's really 6.66 squared. So if you do 100 minus whatever 6.66 squared is, what do you get?
55.6444.
Okay, 55.6444. But remember, that's the value of delta S squared, and we want to know what the value of delta S is. So take the square root of that. And the answer is square root of?
About 7 point.
7.4595?
7.45. How do you like that? So there you go. That's space-time distortion. So Bob is going 2/3 of the speed of light. Bob thinks 7.45 years have elapsed, even though Mary thinks that 10 years have elapsed from this point of reference. All right. So that's the only actual example I'm going to do when there's time for Q&A if you want to talk about others. Kind of the punchline here is, in physics we talk about the fact that not only can you not go faster than light, you can't actually, if you have mass, I have to put some qualification around that. If you have mass, if mass is not 0, you cannot actually go the speed of light. So photons can go the speed of light because photons are massless particles, so mass actually is 0 for them. So they have no problem going the speed of light. But if you have mass greater than 0, you can't go the speed of light. The reason you can't go as fast as or faster than the speed of light is because, in fact, you already are going that fast. As you sit in this room, you are traveling that speed already. But you are putting, because none of you are running around, you are basically putting all of your dollars in making progress through time and no dollars in making progress through space. As soon as you jump in your car and start driving home, you will start investing a little bit of time in making progress through space, and you will trade off a little bit of your progress through time as a consequence of doing that. But remember, if you were on a jet plane doing 500 miles an hour, actually let's make this easier, 1,000 miles an hour, the speed of light is 186,000 miles a second. So so to turn miles per hour into miles per second, you would have to multiply the miles per hour by 3,600. And so you have 186,000 miles per second times 3,600, which if somebody has a calculator, and even if you were going 1,000 miles an hour, that would be a huge number. And so you would be going 1 over that really, really huge number is your fraction of speed of light that you're making. A ridiculously, ridiculously, ridiculously small number, which means that your time skew is also ridiculously, ridiculously, ridiculously small. And this gives us all the illusion that even if we could go 1,000 miles an hour, that there is no time skew. But in fact, there is a time skew, and we can prove it. In fact, this has been proven at least 60 different ways. I'll give you, misconceptions, sorry. One slide on misconceptions, then I'll give you a couple of examples that make this easy. One common misconception is, how many of you have heard of this? Right? Mass increases toward infinity as objects approach the speed of light. Right? It turns out this is not true. By the way, I got a lot of this information from various, a couple of books, and but if you've heard of the Great Courses Plus programs, right? Yeah. There's a couple of excellent, excellent talks. And so a lot of what you're getting here are combined knowledge from some of those talks. Physics professors admit that to help physics students understand some of these concepts, they use a term called relativistic mass. And when the non-physics public hears this term, they assume it means mass. What they're actually trying to convey is this sense of inertia, that as you get closer to the speed of light, it seems as though you are heavier. You are not actually heavier, but it seems as though you are heavier. And so you start to require even greater amounts of energy.
Yeah, you're just requiring so much more force to move, and force is mass times acceleration, so that's...
Right, it's essentially, F equals ma, by the way, is the formula for inertia. So it's basically inertia. It's the reason, by the way, unrelated topic, why when you drop the 1-pound cannonball and the 100-pound cannonball, gravity is in fact stronger pulling on the 100-pound cannonball. That is true than the 1-pound cannonball. And so intuitively you would think that the 100-pound cannonball should fall faster and that Aristotle should be right. But the reason it doesn't happen is because a 100-pound cannonball has more inertia than a 1-pound cannonball, for the same reason why when you go to the grocery store and you have an empty shopping basket, it's really easy to start and stop the shopping basket. It's really easy to make the basket go around the corner at the end of the aisle, right? And after the basket's really full of a lot of food, it's hard to get the basket moving, it's hard to stop the basket, it's hard to corner at the end of the aisle. That's inertia. And so the idea is it's harder to get a 100-pound cannonball to start moving than it is to get a 1-pound cannonball moving because of the force of inertia. And so the extra tug of gravity is precisely canceled out by the extra amount of inertia that it has, and they fall at the same speed. So F equals ma, and the equation for gravity, which is force equals big G over the mass of the big object times the mass of the little object all over the radius squared. If I did that right. Anyway, I might have got that not quite right. But anyway, so that's the idea. So it turns out things don't actually get more true mass. Now, my favorite thing when the public shows up, was outside the Michigan Science Center, and someone came up to me and said, well, you know that relativity has been proven false, and Einstein is wrong about this, right? Relativity, I assure you, has never been proven false. So anybody that walks up to you and says that is simply wrong. Now, I didn't think of this at the time, but she walked away, and about 10 minutes later I went, that's a millennial. I bet that millennial used a GPS app to get down here. If you use a GPS app, the thousands of miles an hour that these satellites are traveling at and at the altitude above the Earth that they're going, relative to how fast you're going on the ground, causes a time skew to occur. And you're like, yeah, but we already talked about that earlier, that the time skew is too small. But when you do these calculations, it turns out, because of the speed of light, all GPS satellites have to send their time pulse at precisely the same moment. So when it's, let's say, 8 o'clock straight up, they all send out a pulse at precisely the same moment. But because one satellite's a little closer to you and one satellite's a little farther from you, you receive the pulse from the nearby satellite, then you receive the pulse. So you're receiving these pulses at different times, even though they were transmitted at the same time. And then you can sort of triangulate where you must be. But this requires keeping their clocks in sync. And if you use a cesium, an atomic clock with cesium, simply taking the clock and raising it 1 meter in altitude will cause it to tick a little slower than the clock that is below it. And this actually has been proven. This does work. So when you do this with satellites, you get this drift. If you could guarantee that your clock and their clocks were precisely the same time when that first pulse came through, by the time that pulse made it to you, the time would have distorted just enough to cause the GPS to think that you were off by about 60 feet. So instead of believing that you're parked in your driveway, the GPS might say that you're over in your neighbor's driveway instead. But that's just the first pulse. And then each time you get another update, the clocks have drifted farther and farther apart. It doesn't take very long before you are miles off course, hundreds of miles off course, thousands of miles off course, and the entire system is rendered worthless. So it turns out, to make the system work, the equations for relativity are actually programmed into the GPS system. And if not for those equations, you would not be able to navigate to find your way around. And that's a guarantee.
The pulses are every second, I believe. So in 1 hour, you'd be 600 miles off course. Or sorry, in 1 minute, you'd be about 600 miles off course.
Tim?
Yeah.
It was my pleasure to be standing next to you that evening when the young lady
Oh,
came
yeah.
up to you. And it was more like 20 minutes. Because you were really ardent about
It took a while.
getting the point right.
It took a while. Because that's the GPS navigation, the GPS navigation case. Here's one, but that's a small time skew. Here's one that's a little more interesting. This one actually did come from the professor on one of the great courses. I love this one, pions. So pions are these things called pi mesons. They're very easy for physicists to create in particle accelerators. The problem with pions is they decay. What's that?
I said, oh, gee.
Oh,
26.
pions decay in 26 billionths of a second. So in 26 nanoseconds, they're going to decay. So if you accelerate a pion to 99.9% of the speed of light, right? If relativity is incorrect, if you take 186,000 miles per second, or whatever unit you want to use, how far will it have gone in 26 billionths of a second? And it turns out the answer is about 25 feet. So I've just drawn this little vector here at 25 feet. But at 99% of the speed of light, if relativity is correct, time should be skewed for the pion. Time should be substantially slowed down. So as the pion is traveling, the pion does not know that 26 billionths of a second have elapsed, because to the pion, they have not elapsed. 26 billionths of a second will not elapse until the pion has gone 557 feet. So the easy way to solve this problem is in your particle detectors, or in your particle accelerator, you're going to put some detectors at different distances from the place where you generate your pions, and you're going to find out how far away can we place our detectors and still detect that the pion is there versus whether the pion has already decayed and we no longer can detect it. And is the answer about 25 feet, or is the answer 557 feet? And all of you should probably guess the correct answer by now. The answer is 557 feet. And physicists can do this experiment all day long. So that's all I have for space-time. If you have any questions, you can start firing away. But if you do have questions, we are trying to record this. So try not to talk over each other, so hopefully the microphones pick you up. Yay! Yes! These can't be hard questions. Go for it.
Yeah, doesn't this depend on your reference frame? Like, we're moving around the sun, 18
Well,
miles.
okay, so,
We're
all right.
moving around the Milky Way galaxy.
So, well, hold on. Yes and no. So first of all, in everyone's reference frame, some observer appears not to be moving. To you, you're not moving. So if you're going 1,000 miles an hour, you are standing still, and everything else is going 1,000 miles an hour. So you can always do the math based on this reference point where you are at the place where nothing is moving, and it's everything else that is doing all the moving. That was one of the concepts of relativity, is that when in all of the thought experiments that Einstein ever did, there is no way to prove who's moving and who is not. It can't be done, right? If I put you in an elevator, or a box, and I drop the box, and so you are following with the elevator, right? But you can't see outside the elevator because it's solid. To you, you're not moving. You just seem to be sitting there. You have no idea that this elevator is hurling because you can't see anything outside of it. So for that reason, it turns out relativity still always works. So one observer always has a reference frame where they get to declare that they are the ones that are not moving, and everybody else is doing all the moving. Yes?
You were expressing inches, feet, and all that.
Yeah.
The science you took when you're using, hasn't everything turned metric now?
Yes. Most physics should always be done in the metric system, and a lot of teachers would say, when you explain things, always use the metric system. Professor Carey Swift next door at U of M says, when I teach my students, everything has to be in the metric system. We don't allow people to mix the stuff. When I go and I talk to, for example, the middle school classes, they're still learning the imperial system.
Why are they?
Why are they?
Is that political, going back to one of our presidents?
I don't know if it's political. I can only tell you that when I was over in the UK, I noticed that they had an interesting way of converting, which was we're only going to convert one unit. So, you know, it was like we're going to go by kilograms now. And they did that for like 5 years. It was like the only thing they ever changed. So everybody only had to get used to one thing changing. And it was like, okay, now we're going to stop using Fahrenheit and we're going to use centigrade now. And so everybody only had to get used to one thing changing. And they were still, when I was over there, still on the miles system. They had not, but they were coming up on the year where they're going to flip that to the, so I'm assuming that they flipped
It's all
that
done.
already.
It's all
Yeah.
the metric system now.
So when we did it in the US, we flipped everything all at the same time, and everyone went crazy because nobody could figure out anything, and they got so frustrated that the FAAC was horrendous, and they said, big mistake, let's just go back to the way it was. And so the
Not
US
all
gave up.
schools only teach the imperial system. A lot of schools do teach the metric system as well. I know my son's school teaches both.
Chris has got a smirk on his face, so I'm going to regret. I'm going to regret this.
I forget the term. I've been out of school a long time, but I always analyze problems by units. Okay, so I know if I divide the units right, I'll come out with the right answer. Well, you were dividing light years by years, which is a little bit of a problem. In the match, you were subtracting it from distance. I mean, I enjoyed your lecture tremendously. I did a great job. All of it I didn't follow,
But speed, whenever you talk about a concept of speed, it's miles per hour, or kilometers per hour, or inches per second. So speed is always conveyed as a distance, a unit of distance per a unit of time. Always, right? That's speed. And so when we're talking about speeds, we can talk about light years per years. Right? So we're allowed to use that as a unit.
you canceled that out.
Correct. Because that a light year per year is a 1 over 1, and 1 over 1 is 1.
Okay.
And so 1 over 1 is just 1. And so anything times 1. Now, if we had done, remember what I said was it's just a conversion factor. So if we didn't do it, we would still see the same distortion ratios, but the number would not have been 7.45 years. We'd have had some other number than 7.45. But the ratios, that part would have worked. We just wouldn't get the right actual answer. But because we use light years per year, we were allowed to get away with 7.45 years. If I said how many days had gone by, our number would obviously be way off because we didn't apply the conversion factor.
Didn't NASA lose an entire Mars probe over this metric, not metric system?
Where
They made one go away. That's a lot of money.
That was a ESA. Yeah, it was an answer.
Was it a similar system for Hubble's optics?
No.
I don't know if that was a.
I think it was something
That
similar.
was something different. That was tactical direction.
I'm over my allotted time. Any other questions, or shall I yield the floor? Okay, if there are no other questions, I yield the floor. Thank you for your attention.
Thank you, sir.